Hello, we are Group 13, and in this short video we would like to explain fluid friction measurements. The main goal of the experiment was to measure pressure drop through an orifice plate and pipes of different roughness and diameters, as can be seen on the screen now. Not only will we walk you through how to carry out this experiment, but we will cover its industrial relevance and explain the data we collected. Now on the screen is a visual of our apparatus.
Moving to the experimental procedure. Firstly, we will alter the flow rate of water to either high, medium or low flow rate, and this can be done by opening and closing the tap. For the second step, measuring the flow rate of water, we will use the foam ball as a stopper, which will allow us to measure the flow rate at that specific setting by measuring the time taken for the volume of water to reach 5 liters. And the quotient of the volume over the time taken will give us the volumetric flow rate in meters cubed per second. For the third step, measure the pressure drops across a pipe and record an average value using digital manometer. First, we need to make sure that only the pipe being measured is open and the rest are closed, and then we'll use the tubes connected to the manometer and connect them to the pipe being measured. And we will turn the digital manometer on and finally record the pressure drops shown by the digital manometer, and an average will be taken as the value will be fluctuating. Finally, repeat the previous steps for the 3 pipes at high, medium and low flow rates. And this is a photo showing 2 of the smooth pipes with diameters of 10.9 millimeters and 17.2 millimeters, and 1 rough pipe with 17 millimeters.
Now you might be wondering, why is this important? In industry, engineers use friction losses from fluid friction experiments to choose the right design parameters for pipes and valves, which can make an industrial process more efficient and more safe. The experimental data is crucial when it comes to the design of pipelines and water distribution networks, for example. Some key industries that you may be familiar with that employ knowledge on fluid friction include product testing in the paint industry to ensure the product performs well in various settings and environments. Another key industry is the pharmaceutical industry, where knowledge on fluid properties is vital for safety and to ensure proper mixing and production. By measuring changes in pressure drop over time, potential fouling can be spotted in a process. Fouling can occur when suspended particles in the fluid settle on heat exchanger surfaces, a phenomenon very common in wastewater treatment, for example. These deposits act as a source of resistance which can be seen through a pressure drop. This is one example as to where fluid friction can be used in industry to regulate but also innovate real-life solutions.
Here are the data collected for flow rates and pressure drops. By plotting the flow rates against the square root of the pressure drops, we obtain a linear relationship with the equation indicated on the graph. Using the slope of this equation, we can find the discharge coefficient of the orifice plate. On the right, we can see the formula used to find the discharge coefficient of the orifice plate, with m being the slope of the graph obtained earlier. On the left, we can see the formulas used for experimental and theoretical approaches for the smooth and rough pipes. Here is a bigger picture for the Moody diagram to calculate the friction coefficient of the rough pipe. For the experimental results, the discharge coefficient was found to be 0.18, which is 5% greater than the value calculating using the theoretical equation. This value is affected by several factors, which can be the geometry of the orifice plate and the flow conditions. Here we can see the values of the friction coefficients of both smooth and rough pipes, and as we can observe, moving from small to big diameters, the friction coefficient increases, while moving from low to high flow rates, the friction coefficient decreases. And this relationship is proved by the inversely proportional relationship between the friction coefficient and Reynolds number. So as Reynolds number increases, the friction coefficient will decrease.
To conclude, pressure drops are calculated across orifice plates and various pipes. This is done to calculate the fluid friction coefficient of pipes and the discharge coefficient of an orifice plate. It can help one to understand the fundamentals of fluid dynamics, specifically fluid flow and behavior. From the experiment, one can start to think about how the following principles can be applied in the chemical engineering industry. Thank you for listening.